Okay, so first, to solve this differential equation, we're going to have to separate the variables. So we'll multiply both sides by dt, and then divide both sides by p times 1 minus p over 4,000. So we'll get dp over p times 1 minus p over 4,000 equals k dt. And of course, we'll take the antiderivative of both sides. So we try to take the antiderivative of this, or maybe take a natural log, but then if it's product of functions, maybe we'll multiply p in there, but then we'll just get p minus p squared over 4,000. That doesn't work for the log rule. So what we'll do is we will rewrite this. First, let's just agree that this is the same. Over 4,000 dp, right? Just that fraction there. This side's easy. This side's done, right? Well, what is the antiderivative of a constant times dt? It's just k times t, right? Because if I take the derivative of kt, I'll just get k, whatever that is. Right. Just remember that k and well, k is just some constant that we're trying to find. So next, looking at this, I could take the derivative of like 1 over p plus 1 over that, right? But I can't really do that. If it was a sum, I could break it apart as a sum, then I could take two different integrals, but I can't take apart a product. Like I can't take this as the integral of 1 over p dp times the integral of, you know what I'm trying to say? Because it doesn't work that way. An integral is an infinite sum, so you can split apart sums, but not products. So, differential or partial fractions time 1 over p times 1 minus p over 4,000. Remember, partial fractions says if only this looked like something over p plus something else over 1 minus p over 4,000. If only. Well, if that were true, we could solve for a and b. We could do something simple like multiply both sides by this denominator. On this side, you get a cancellation. You get 1. On this side, the p would cancel this p and leave us with a times 1 minus p over 4,000 plus b times p. Now how to solve for a and b? Well, this is an equation here, right? It's true. It's true. It's true for some a and b, and for all values of p. Whatever p happens to be, it's true for that value of p. So I come down to this equation, and I say, what if p equals 0? If I do that, then this term goes away. I'm left with a times 1, right? Because 1 minus the p is 0, that makes this 0, so all that's left here is a 1. So a times 1 equals 1. So I'm going to put like this, a is 1. Okay, let's do the same thing. We'll solve for b in a similar way. P over 4,000 plus b times p. All right, so we made this go away by making b multiplied by 0. So what would we plug in here to make that happen? Will that be 1 minus 1? So I would put 4,000 in here. Put 4,000 here. And you can see that b is going to be 1 over 4,000. 1 over 4,000. And just a quick note here, now this fraction is 1 over 4,000. Let's just make this a little simpler. Okay, let's multiply the numerator and denominator by 4,000. Here it cancels out the 4,000, we're left with 1. Here we get 4,000, and the 4,000 cancels here, and we just get minus p. Okay, so this guy becomes 1 over p plus, right, 1 over 4,000 minus p dp. And this side is kt, as we already discussed. And don't forget the plus c. Okay, so we take the antiderivative of both sides, take the antiderivative of this, you get natural log of the absolute value of p. For this one, let u be 4,000 minus p, and then du will be negative dp, so we'll have this negative natural log of the absolute value of 4,000 minus p equals kt plus c, exponentiate, oh no, we don't want to exponentiate yet, we want to use the properties of logarithms to put these together. P over 4,000 minus p equals kt plus c, the natural log, now we exponentiate both sides, and we get p over 4,000 minus p equals e to the kt plus c, which equals e to the kt times e to the c. And we'll just make this number right here, we've talked about this before, we'll just call it b, because that's what the book calls it, so we might as well stay consistent. We get p over 4,000 minus p equals b e to the kt. We still are trying to solve for p here. Let's clear this out of here. Make some more room. So multiply both sides by the denominator, of course. We'll get p equals b e to the kt times 4,000 minus p. We'll distribute this guy. We get p equals, I guess maybe I should do like 4,000 b e to the kt minus p b e to the kt. And we'll add this to both sides, p plus p e to the kt, or p b e to the kt equals 4,000 b e to the kt. And we'll factor out this p and then divide, so you know what that's going to be like. We get 4,000, so close to being sort of done with this, over 1 plus b e to the kt. And now it looks like, hey, we're kind of done. But let's just, instead of having two instances of e to some power, let's just multiply both the numerator and denominator by e. Actually, let's see. Times one, I guess this will be a little kind of silly, but 1 over b e to the kt. And we'll multiply this by 1 over b times e to the kt. We'll cancel out b e to the kt here in the numerator, so we're just left with 4,000. Over, we'll distribute this through the denominator here, so we'll get 1, let's just start it as 1 over b times e to the negative kt plus 1, because it's going to cancel out there. And this 1 over b, right, it's just some constant, so we'll just give it a, let's call all these b's b1s, right? Okay, so then we just call this 4,000 over b, some constant, times e to the negative kt plus 1. Okay, so there is our differential equation solved. And now we can go about trying to find the particular solution for the given populations that they told us about. That's it for this video. Thanks for watching.